then this is Bessel's equation of the zeroth order. But this is not Bessel's equation of the zeroth order. It comes about to look like this because of the quirk of cylindrical coordinate system. Okay, F1, F of K rho. And if you expand this out, this actually will be written as 1 over rho partial rho, rho partial rho, plus 1 over rho. Okay, you write it out. It can be written out as such. Very simple, just write this to look like Bessel's equation, but you find that you have extra 1 over rho. And Bessel's equation of nth order looks like this with an n here. This Bessel's equation of nth order. But since the quirk of this being in cylindrical coordinate system 61, so you should plug in J1 for part B. Okay, that's simple, right? It's not that mysterious.
You can find out Wikipedia.
What is that?
You can find out Wikipedia.
What B is?
What the eigenmodes were of that operator.
Eigenmode? Well, this is just Bessel's equation. This equation is Bessel's equation of the first order.
Yeah, but Wikipedia didn't tell me that.
Wikipedia has it in Cartesian coordinates.
Oh, Wikipedia. Don't rely on Wikipedia.
How are we supposed to know that?
Or even Wolfram Alpha doesn't have it.
Well, you know that this has been Bessel's equation all along, right? Take 520, 350, 450 something. This has always been Bessel's equation, but this is not Bessel's equation. It doesn't look like Bessel's equation. So you have to make it look something like this. Bessel's equation of an nth order have something like that. Look something like this with an n over rho. Maybe minus, sorry, minus. Minus n squared, sorry, n squared. Okay. Bessel's equation of n order. Oh, sorry, rho squared. Things start to come back to my memory now. As I write more. Between n squared over rho squared. Bessel's equation of the nth order. Okay. Then everything will work out correctly.
Yeah, so why n equals to 1 like in this case?
Well, because if you expand this out to make it look like that, there's a 1 over rho squared term.
Yeah, I know, like, but why we got like at the bottom one effort for this?
Well, because this actually is equation not for x, y, z, is for this field component. As I say, this field component does not satisfy the Cartesian Laplacian. Okay, I think somewhere in my homework, asked you to prove that you cannot write down the Laplacian, ordinary Laplacian for the field component of the field. Neither can you do that for the rho and the other components. They will satisfy a very strange looking Laplacian. Okay, and this is why it's strange looking. Okay? Okay, I think you guys rely too much on Wikipedia. It's a problem. Okay. So let's go back to this thing again. And so this saddle point is wonderful, and you can sketch the direction of the ski slope. It will go something like this. Okay. And then what about the ski slopes next to this saddle point? Think of this as a mountain pass, Khyber Pass. Okay, or some of the passes you know in your geography lessons. Okay. Then the steepest direction of steepest descent will look something like this, around this saddle. It will look something like this. Okay? And then it will look something like this. Agree? This is how a saddle point. A saddle looks like horse saddle. Okay, horse saddle looks like. And if you want to sketch the constant amplitude contour, it will look something like this. It will look something like this, but I wouldn't sketch those things to confuse you. This is the direction of steepest descent. And what it says is that as lambda gets very large, you have to learn how to identify critical points of the integrand. And there are only two important critical points for this integrand, which is the saddle point and the pole. As lambda becomes very large, only those 2 points are contributing to the integral. The others are not important. Those 2 points are called the critical points. Okay. So what happens if I have, say, a semi-infinite integral? Say if I have an integral that's semi-infinite, how do I identify the critical point? Say if I have an integral that is, say, going like this, say, semi-infinite. That's my C. Okay? I still would have this as my stationary phase point, the setup point, and then I will have a constant phase path that passes through it. Okay? And then if I do the mapping now, this is complex T plane. Okay, this is a complex T. Let's assume that the pole is not there. Let's try to identify what the critical points of this integral is now. So I go to the complex S plane. This P maps to P prime. Okay, which is this over here. And this C probably maps to something that looks like this. Maps to something that looks like this. C prime. Okay, and then this point T maps to this. Somewhere over here. Okay. So, if I look at this path over here, how could I deform this path to that path now? There's a difficulty, right? Before that, I have an infinite path, and I can easily deform this path, and things are exponentially small at the end. I can, by Jordan's lemma, argue that things are zero. But I would have a great difficulty to deform C prime to P prime in this one. So what shall I do? Well, I can do the deformation by adding more paths. I can add paths such as this one over here. I know that the direction of steepest descent looks something like this over here. Okay, around the setup point. So I'm going to add one more path. That is also a steepest descent path, which means that this path will look something like this. It follows the direction of steepest descent. Okay? Let me call it S. If I were to add this path, let's assume that this goes to 0 and infinity, so I can close this path quite easily. So I can say that integrating along C prime is the same as integrating along S plus integration along T, and then I can close this path, and that equal to 0. So C prime is equal to S plus P prime. Okay, integrating along C prime is integrating along S plus P prime. Can you see that? Okay. S starts from this point, this endpoint. This endpoint maps to this endpoint. Okay? This endpoint maps to this endpoint. This is might be PE or something like this, mapped to this point over here. So S will start from there, follow the direction of steepest descent that I have mapped out, and then so I can actually do this contour deformation. So my final integral is just S plus P, but where is the contribution to S is going to come from mainly? S is going to be a steepest descent path. As lambda gets bigger, the rate of descent becomes higher and higher. So if I were to integrate along S, where would most of the contribution come from? From this point, right? From the end point. Because this is the direction of steepest descent. So as lambda gets bigger and bigger in this picture, there are two critical points that will contribute to this integral, which is the setup point plus the end point. Those are the two things. So I want you to be able to identify these critical points. For that one is that one, if there's a pole, is that one. For integration with endpoints, is the endpoint integration plus the setup point. Okay, those are the two things I want you to remember. Does everybody get it? Okay. So we can go and do some examples then, if you get this. Well, actually, according to the Western calendar, today is full moon. But according to the Chinese calendar, yesterday was full moon. So I don't know which is full moon. So, but it's the Mid-Autumn Festival, either today or yesterday. Okay? So happy Mid-Autumn. Okay. Happy Mid-Autumn Festival. So let's go back to doing mathematics again, okay? Yeah.
I think we do know, like, at first we don't know where the line is, like, I mean the P line. And how do we know, like, whether or not, like, there's a pole in that?
Okay, very good. I did not address this issue. How to find the line P? You find P by solving this equation. So you solve this equation T as a function of S by using some either numerical method, if this cannot be inverted. If this is an invertible function, you can find T of S is, say if you know how to invert this function. Okay, you invert this function, then you can find T very easily. And then you just plug in values of S on the real axis here. Real values, and then solve for your T. Okay, solve for your T. And then you can find your P. And then you can map, you have to oftentimes map this out numerically. Sometimes it's not found in closed form. Okay, you have to map out numerically, and it's something that I didn't address. Thank you for pointing that out. That is what you need to do to find your P. Okay. So everything is quite rigorous in this method. As you can see, more rigorous than the hand waving stationary phase method. And let's do some examples. Okay, so let's say that we end up with this integral, and then we just have to evaluate the integral as accurately as we want to, and most of the contribution to that integral will come from the startup point. So the natural thing to do then is to actually evaluate this integral by Taylor series expansion. And I will let f of s be written as a Taylor series expansion, s of n. I will Taylor series expand around the origin because that's where most of the contribution will come from. And I would say that this Taylor series expansion is from 0 to infinity 1 over n factorial, right? If I did my Taylor series expansion correctly. And then I plug that in, and I just do my simplify I. I'm not going to carry that e to the I lambda ht naught around because it's a constant. And then I would have, I just want to figure out how to evaluate this. Then I plug this in, and then exchange the order of integration and summation. The s to the n e to the minus lambda s squared, right? But what did your mathematics teacher tell you? The do's and the don'ts of exchanging orders of integration and summation.
Only if it's convergent.
Only it converges, right? Only after exchanging the integration and summation that this thing still converges. Okay? Another way to look at it is that if this Taylor series expansion converges everywhere along this path of integration, then the exchange of integration and summation is legitimate. And usually it will converge. But it turns out that this Taylor series expansion does not converge everywhere on the complex plane. Why is that so? Does anybody have enough memory of your complex variables knowledge to tell me why that Taylor series expansion does not converge everywhere on the complex plane? What is the radius of convergence of that Taylor series expansion? Something that harks back to your complex variables knowledge. Yeah? 1. It converge. It has a radius of convergence of 1. Is that what you say? Why? N factorial is extremely powerful, right? N factorial is a very powerful number. N factorial is almost like n to the n, right? When n is very large. What is the formula for n factorial? Do you remember what the formula? When n goes to infinity? Stirling formula. Does anybody remember Stirling's formula?
So, and
What?
there's an over
Log of
and
Log of this is?
so and
So it's some, I don't remember Stirling's formula. I probably remember something like you too. Log of this is some n. So it's roughly n to the n, but I forgot whether it's half power or something. You know, quite powerful number. So n factorial grows quite fast. So you would think that that series has a good chance of convergence. But it does not converge everywhere on the complex plane. The complex variables theories will tell you so. What limits the convergence of that function? Do you remember? Just a simple Taylor series expansion. They don't converge everywhere on the complex plane. Yes, Mike, you just took complex variables last semester.
Wait, what are we expanding? E lambda S?
This one, what is the radius of convergence of this Taylor series expansion on the complex plane? I'm just expanding this function on the complex plane around the origin.
Wait, so we Taylor expanded at the exponential of the whole thing? Of the
No,
whole
just the function, the slowly varying part of the function. This is rapidly varying, this is slowly varying. And we expand this.
I don't know.
I'm surprised your complex variables teacher never taught you this. That a Taylor series expansion has a radius of convergence. The radius of convergence is dictated by the nearest singularity
Where's the pole?
point, the pole.
But isn't it S to the n and all the n's are positive?
So it cannot have the radius of convergence larger than this distance.
Oh,
Okay, this is the radius of convergence. It can only converge within this disk on the complex plane. Everybody knows that, right? Now old memories start to come back. But they did not, you never learned this before. Okay? So that series is actually not everywhere convergent on the real axis. It only converges within that disk, and hence it only converges within the part of the disk that overlaps with the real axis. So for that reason, the exchange of order of integration is not legitimate, but we do it anyhow. Okay, we do it anyhow, but I should say that this is not exact. This should be an approximation. And actually what happens is that if you look at this thing over here, this is s to the n e to the lambda s, right? E to the lambda s looks like this, but this thing looks like this. S to the n e to the minus lambda s squared. So in total then, the whole thing looks like this. This is a product. The integrand looks something like this. As n increases, what happened to this peak? The two peaks move further and further out as n increases. So you can get by with this in the first few terms of this series. Because in the first few terms of this series, the contribution is still coming from very close to the origin, and hence still within the radius of convergence of the series. But as you go to higher and higher terms, as n becomes larger, the peak of the integrand actually becomes further and further away. This moves up when n increases. Right, you can look at this picture. So what it tells you is that this series is useless after a while. It actually just brings in garbage as n becomes big, because you're trying to look for terms outside the radius of convergence of the series. And then, so this kind of series is called a semi-convergent series. Only the first few terms are important and useful. You can see from here, okay? But the high order terms are useless because they are starting to bring in contribution from outside the radius of convergence of this Fourier series, which is not legitimate. So this is also called an asymptotic series. So as lambda goes to infinity, you can bring these two. If you think of lambda as being a large number, you also bring the two peaks closer and closer. But as n increases, they're actually competing with each other. Large n tends to make these two peaks far out. Large lambda tends to bring them back in. So the number of terms that are useful in this series becomes larger as lambda gets bigger. Okay. But finally it diverges. So this series finally diverges. And you can look at all asymptotic series that you obtain in this manner. They all eventually diverge. Okay, but the first few terms are useful because they bring in contributions from within that radius of convergence. Okay, so these are some of the points I want you to notice. And then another thing I want to say about this thing is that what happens when n is odd? When it's 0, right? This term only contributes when n is even. So finally, only the even power or even order derivatives of this power series contribute. The odd powers don't contribute. Okay. So this all worked out in the textbook. I wouldn't work out the details. But I want you to remember these few things. Critical points. How to identify critical points. So let's do some examples on how we can find critical points for sum of our integrals. And then you can apply this asymptotic expansion techniques, which are rigorous, but bear in mind that this series are semi-convergent. They eventually will diverge. Okay, let's look at the sum of an integral that we have. So let's look at the vertical magnetic dipole. Or VMD case. Okay, in that case we work with HZ instead. And then we work with HZ, the reflected wave term will look something like this. Very similar to the VED case. Everything is here K rho over K13, H01 K rho. And then we have this R12, but just TE reflection coefficient now instead of TM. And then e to the I K1Z D plus 2D1. Okay, this is how the integrand will look like for the reflected wave term alone. And then R12 is rather complicated looking. If you assume mu1 equals mu2, which is non-magnetic material, then it's rather simple. So there's no occasion for the existence of poles in the denominator. We make this case simpler because there will be no poles in the denominator. And then if you look at the complex plane, what you have in the complex plane is rather complicated, because then you have to figure out what the singularities and where they are. There will be branch point singularities. And usually these singularities are critical points, like the poles, the branch points, the end points of the integration. Those are critical points, okay? Branch point singularities. Where are the branch point singularities for this integral, or this integrand? Remember that k1z is equal to square root of k1 squared minus k rho squared. k2z is equal to k2 squared minus k rho squared. So there are branch point singularities at k rho equal to plus or minus k1, k rho equal to plus or minus k2. Okay. And I deliberately choose the case so that Brewster angle cannot exist, neither could the pole exist. Okay, so there are no pole singularity for this. And so we can identify now the branch points and the branch cuts. And we already learned how to do that for the simple sum of an integral. Now we have a more complex one. So there are branch points here, k1, and there would be one at minus k1. And then there will be another one at k2, and let's assume that k2 is larger than k1. And then there will be one at minus k2. And next we need to draw the sum of the branch cuts that are associated with these branch points. And we learned how to do that in the last lecture. They look something like this. They look like a rectangular hyperbola. Okay, and then there's another one that goes like this. This is the imaginary k1z equal to 0 branch cut. It looks something like that. Okay, and then there is another branch cut that goes through the k2 branch point. It will also be a rectangular hyperbola. And let's assume the loss is very small. This would be imaginary k2z equal to 0 branch cut. And the other one will look something like this. Okay. And then we look for the setup point. The setup point is given by this exponential function plus this exponential function. The setup point is the same as the stationary phase point. We already found that before. The setup point is given by this thing over here. We did that. And let's call this theta I. Okay, we did that before. For the sake, does everybody remember this? Right? So it should be somewhere less than k1. Okay. And then the next thing we need to do is to find the constant phase path that passes through the setup point. And you go through that by solving this equation. Remember, I say if you solve this equation, you do this mapping. you find the constant phase path. So you go through this thing and write your lambda ht has been equal to k rho. Actually, it's a function of k rho on a complex k rho plane plus k1z z plus 2d1, and then you minus the value of this at the saddle point, which is actually just k1 ri. Okay, ht naught is just equal to that. I want to explain why, but if you evaluate that, it would be equal to that. Equal to minus s squared. So the left hand side should be equal to minus lambda h k rho s plus this. Okay, it's kind of not very clean, but you know what I mean. Okay, you solve that equation to look for the constant phase path that passes through the saddle point, and that equation you have to solve numerically. There's no closed form. I don't believe that there's a closed form solution to this. Maybe there is, but not easy closed form. Okay, so I think I showed you that this can be written as k1 cosine of alpha minus beta I. I think a while back you helped me show that this is true. So you can solve this equation for every s, you solve for your alpha, and after you have found your alpha, then you find your k rho is k1 sine alpha. You can solve that equation almost in closed form, not in closed form. You have to probably use MATLAB to help you. Okay, and the constant phase path turns out to be like this. You look something like this, like this. Goes to the next Riemann sheet, causes the branch cuts. Okay, after you have solved it numerically, don't ask me why it looks like that, but that's what you find after you do it numerically. And then these two asymptotes. These two asymptotes are theta I. Okay. And then it crosses the other point over here as k1 over sine theta I. Okay, and then you can actually prove that from these equations also. But that is the steepest descent path, the constant phase path that passes through the saddle point. Okay. How can we deform the original path, which is a summerful integration path? This is the SIP. How can we deform the SIP to this, what I call the constant phase path 1? Okay, how can I deform that? It's not easy, right? It's not deformable. We live in two different worlds because I can deform this path to this path. I said the integration along the summerful path is like this. But then I can integrate along and then I can cross the branch cuts. I want to maintain analytic continuity. I always go to the lower Riemann sheet. So I go to the lower Riemann sheet of the first cut, and then I go to the lowest Riemann sheet of the second cut. So over here I'm at the bottommost Riemann sheet, because I'm the bottom sheet of both cuts. And then as I over here, when I cross one branch cut, I emerge from the bottom Riemann sheet of one of the cuts, and then I emerge from the other bottom Riemann sheet of the other cut. And here I see the daylight again. I'm at the top Riemann sheet again. Okay. But here I cross the branch cut once. I would be at the bottom Riemann sheet of this cut. And then I go to the never land, and there's no way that I can meet up with this guy over here. These are on different worlds. So there's no way I can close this path by contour deformation. However, I can do one more thing. I can add paths so that I can close the contour. So if I add a path that looks something like this, bottom Riemann sheet, I look for the steepest descent path or the constant phase path that passes through this branch point. It will look something like this. Okay, this is what it is on the bottom Riemann sheet. And then it looks like this on the top Riemann sheet. This is the steepest descent path, SDP, that passes through this branch point K2 on the top and the bottom Riemann sheet. You see the SDP, or the constant phase path, is only determined by this equation, or this equation that depends on K1z. Does not depend on K2z. So it doesn't matter whether I'm on the top or the bottom Riemann sheet. The SDP for that passes through the branch point K2 looks the same, but except that they're on a different Riemann sheet of K2. See? Okay, so if I add the additional path, this goes to the never land, but I can turn around and pick up this path at infinity and comes back here. So I can keep marching like this, and then keep coming back from infinity along this path. And then this is on the top sheet. Now I can close up and meet up with this guy over here. The SIP and my path meet each other. Then that forms a closed contour.
How did you get that last part?
What is that?
How did you get that last part? Like how did you close the
Yeah.
HT here?
Yeah, it goes to infinity,
No,
right?
You closed it there, right?
Yeah, I can add this part because